Hello and welcome back at the IPv4 addressing. This material is divided in 3 parts, and all of those parts we are covering the fundamental aspects of IPv4 addressing in detail. At the first video, we described the structure of an IPv4 address, including the network portion, the host portion, and even the subnet mask. We even compared the characteristics and uses of the unicast, broadcast, and multicast IPv4 addresses, and we also explained the public, private, and reserved IPv4 addresses. So in this video, we will be focused at explaining how the subnetting segments a network to enable better communication, how to calculate IPv4 subnets for a /24 prefix, and even to calculate the IPv4 subnets for a /16 and /8 prefix. And the subnet to meet requirements, variable length subnet mask, and structure design will be at the third video. Have you ever received an email that was addressed to every person at your work or school? This was a broadcast email. Hopefully it contained information that each of you needed to know, but often a broadcast is not really pertinent to everyone in the mailing list. Sometimes only a segment of the population need to read that information. In an Ethernet LAN, devices use broadcast and address resolution protocol, as we explained in the other video, to locate other devices. Address resolution protocol sends layer 2 broadcasts to a known IPv4 address on the local network to discover the associated MAC address. Devices on Ethernet LANs also locate other devices using services. A host typically acquires its IPv4 address configuration using the Dynamic Host Configuration Protocol, which sends broadcasts on the local network to locate a DHCP server. Switches propagate broadcasts out of all interfaces except the interface on which it was received. For example, if we see the figure if the switch in this figure were to receive a broadcast, it would forward it to other switches and other users connecting in its network. Routers do not propagate broadcast. When a router receives a broadcast, it does not forward it out other interfaces. For instance, in this figure, when the router 1 receives a broadcast on its Giga Ethernet 0/0 interface, it does not forward to another interface. Therefore, each router interface connects to a broadcast domain, and broadcasts are only propagated within the specific broadcast domain. A large broadcast domain is a network that connects many hosts. A problem with a large broadcast domain is that these hosts can generate excessive broadcasts and negatively affect the network. In the figure, there is the LAN 1 with the IP address of 172.16.0.0/16 and connects 400 hosts that could generate an excess amount of broadcast traffic. This results in slow network operation due to the significant amount of traffic it can cause, and slow device operation because a device must accept and process each broadcast packet. The solution is to reduce the size of the network to create smaller broadcast domains in a process called subnetting. These smaller network spaces are called subnets. And here in the figure, the 400 users in LAN 1 with the network address of 172.16.0.0/16 have been divided into subnets of 200 users, and each one with the IP of the network 172.16.0.0/24 and the other one 172.16.1.0/24. Broadcasts are only propagated within the smaller broadcast domain, so we created 2 broadcast domains. Therefore, a broadcast in LAN 1 would not propagate the broadcast to LAN 2. And you can see that even the prefix length has changed from a single /16 network to 2/24 networks. This is the basic of subnetting, using host bits to create additional subnets. Subnetting reduces overall network traffic and improves network performance. It also enables an administrator to implement security policies such as which subnets are allowed or not allowed to communicate together. Another reason is that it reduces the number of devices affected by abnormal broadcast traffic due to the misconfiguration, hardware-software problems, or even malicious intent. There are various ways of using subnets to help manage network devices. We can create subnet depending on the location, as you can see in this figure. In the building has 1, 2, 3, 4, 5 subnets, where each subnet is for a specific floor of the building. We can create subnet even by the group on function, and as you can see here, there are 4 groups, and in each group has its own subnet divided by the responsibilities of the workers at the organization. We can even create subnets divided by the type of the devices. And as you can see here, there are 3 groups of the subnet, where at the LAN 1, at the first subnet, are all hosts. And at the LAN 3, at this subnet, are all the server devices, and at the second group are all the printer devices. And network administrator can create subnet using any other division that makes sense for the network. The subnets are longer prefix lengths to identify networks. Understanding how to subnet networks is a fundamental skill that all network administrators must develop. Various methods have been created to help understand this process. Although a little overwhelming at first, you will pay close attention to the detail, and by practicing, subnetting will become easier even for you. At the previous slides, we learned that there are good reasons for segmenting a network. We even say that segmenting a network is called subnetting. Subnetting is a critical skill to have when administrating an IPv4 network. IPv4 subnets are created by using one or more host bits as network bits. This is done by extending the subnet mask to borrow some of the bits from the host portion of the address to create additional network bits. The more host bits that are borrowed, the more subnets can be defined. The more bits that can be borrowed to increase the number of the subnets will reduce the number of hosts per subnet. Networks are most easily subnetted at the octet boundary of /8/16 and /24. And here at the table, there are identifies this prefix length with the subnet mask and the number of hosts for each of these prefix length. And you can see that by using longer prefix length, will decrease the number of hosts per subnet. And for each prefix length, there is mentioned the subnet mask and which octet is for the network and which octet is for the host portion. To understand how subnetting on the octet boundary can be useful, let's consider an example, and let's assume that there is an enterprise choosing the private address of 10.0.0.0/8 as its internal network address. The network address can connect around to 16 million hosts, but having more than 16 million hosts is not a single subnet and not ideal. The enterprise could further subnet the 10.0.0/8 address at the octet boundary of /16 as it is shown here. You can understand that by going from this octet, by this address with this subnet mask to /16, it means that you are going from this subnet mask to this subnet mask, and it means that you are borrowing this octet from the host portion to create subnet. And here at the table you can see that it will define up to 256 possible subnets that will start from 10.0.0.0/16 to 10.255.0.0/16. And here at the second one, you can see that there are the host range for each subnet and even the broadcast for each of those subnets. You can see that the first two octets identify the network portion of the address, where the last two octets are for the host IP address. The enterprise could choose to subnet the 10.0.0/8 network at the /24 octet binary as it is shown in this table. This could send us to the possibility of 65,000 subnets, and by going from here /8 to /24, it means that you are borrowing 2 octets from the host portion to create subnets. And here it is listed the first subnet, and here is the last subnet, and the host range for each of those subnets, and even the broadcast for these subnets. The examples shown at the other slide before were borrowing host bits from the common /8/16 and /24 network prefixes. However, subnets can borrow bits from any host bit position to create other masks. For instance, a /24 network address is commonly subnetted using longer prefix lengths by borrowing bits from the fourth octet. It means by borrowing bits from the host octet. This provides the administrator with additional flexibility when assigning network address to a smaller number of end devices. Refer to the table, we can see that there are 6 ways to subnet a /24 network. And by subnetting this, it means that we can go from /24 to /25 by borrowing 1 bit at the host portion, and we can go to this subnet mask. By borrowing 1 bit, it means that we can create 2 subnets with 126 hosts for each of those subnets. By borrowing 2 bits, we can go to this subnet mask, prefix length with this subnet mask, and with 4 subnets with 62 hosts for each of those. And let's go to the last one, to the 6th way of creating subnets. We can go to the /30 with this subnet mask. It means that we have borrowed 6 hosts from the host portion to create subnet. And by borrowing 6 hosts, it means that we can create 64 subnets with 2 hosts for each subnet. Some subnetting are easier than other subnetting. We will explain how to create subnets that each have the same number of hosts. In a situation requiring a larger number of subnets, an IPv4 address network is required that has more host bits available to borrow. For example, the network address 172.16.0.0 has a default mask of 255.255.0.0 or /16, and this address has 16 bits in the network portion and 16 bits in the host portion. The 16 bits in the host portion are available to borrow for creating subnets. And here at this table is highlighted all the possibility scenarios for subnetting a /16 prefix. Here is the prefix length that will grow as you borrow bits from the host portion. Here is the subnet mask, and here are the subnets that you can create by borrowing these bits, and the number of hosts available for those subnets. And as you can see, as more bits you can borrow from the host portion, more subnets you can create, but with less hosts available for each of the subnets. You don't need to memorize all this table. The only things that you need to understand is that how each value in this table is generated. The reason is that it has 8 additional bits that can be borrowed, and therefore the number of subnets and hosts are simply larger. Sorry, there are 16 additional bits that can be borrowed, not 8. Let's consider a large enterprise that requires at least 100 subnets that has chosen the private address of 172.16.0.0/16 as its internal network address. When borrowing bits from a /16 address, start borrowing bits in the third octet going from left to the right. Borrow a single bit at a time until the number of bits necessary to create 100 subnets is reached. Here in the figure, it is displayed the number of subnets that can be created when borrowing bits from the third octet and the fourth octet. You can see that there are up to 14 host bits that can be borrowed. So, as said, start borrowing from the third octet from the left to the right. And for every bit that you are borrowing, calculate the number of hosts that you can create. The number of hosts that subnet that you can create can be calculated at this form. The base, number 2, will be exponential by the number of bits that you can borrow. So if you are borrowing 1 bit, 2 exponential by 1, you can create 2 subnets. If you are borrowing 3 bits, 2 exponential by 3, you can create 8 bits. So here you can see that for creating 100 subnets for the enterprise, you need to borrow 7 bits. By borrowing 7 bits, you are able to create 2 exponential by 7, 128 subnets. By borrowing 7 bits from the host portion from the third octet, it means that you have to change even the subnet mask that reflect the borrowed bits. And here it is shown the subnet mask that will change at /23, because remembering that the subnet mask shows the network portion. And by doing that, here are displayed the resulting subnet from 172.16.0.0/23 to 172.16.254.0/23. After borrowing 7 bits for the subnet, there is 1 host bit remaining at the third octet and 8 bits remaining at the fourth octet, with a total of 9 bits for the host portion. With the 9 bits for the host portion, we will be able to create 2 exponential by 9 bits remaining at the total of 512 host addresses. But remember that the first host address is reserved for the network address and the last address is reserved for the broadcast address. So by subtracting those two, we will have 510 available host address for each /23 subnet. And here in the figure, it is shown the first and the last host address for the first network address. And remember that the first host address is at the all bits at the host portion will be 0, different the last one that will be 1, and the last host address will be all bits 1, only the last one will be 0. And as the broadcast address, all the bits at the host portion will be 1. And by referring to this, we have the first host address as 172.16.0.1/23. The last host address will be 172.16.1.254/23. And the broadcast address will be 172.16.1.255/23. Some organizations, such as small service providers or large enterprises, might need even more subnets. Let's take a small internet service provider that requires 1,000 subnets for its clients. Each client will need plenty of space in the host portion to create its own subnet. The internet service provider has a network address of 10.0.0.0/8. That means that there are 8 bits in the network portion and 24 hosts available bits to borrow towards subnetting. Therefore, the small internet service provider will subnet the 10.0.0.0/8 network. To create subnets, you must borrow bits from the host portion of the internet IP protocol version 4 address of the existing network. Starting from the left to the right, with the first available host bit, borrow a single bit at a time until you will reach the number of bits necessary to create 1,000 subnets. And here in the figure, it is shown that you need to borrow 10 bits to create 1,024 subnets, because 2 exponential by 10 bits that you will be created will give you the results of subnets that you may be able to create. This includes 8 bits in the second octet and 2 additional bits from the third octet. It means that you are borrowing at those 2 octets. You started at the second octet and you went to the third octet by borrowing 2 more there. By borrowing 10 bits at the host portion for creating subnets, it means that you have to extend even your subnet mask that represent the network portion, and by this it means that all of those 10 bits will be extended and will be with 1 to represent your subnet mask, and the subnet mask will go to 255.255.192.0 or just /18. And as we mentioned, we can create 1,024 subnets by borrowing those 10 bits. And here it is displayed the specific of the first subnet, the network address, first host address, last host address, and even the broadcast address. And this was the second part of the IPv4 addressing. Thank you for being with me. Do not forget to subscribe at my YouTube channel for those who are new at this channel, and hit the notification button for all the videos that will come up. Thank you.